The birth of modern cosmology. The history of our understanding of the universe begins with the profound change in perspective that took place in the early 20th century. Before this time, the universe was considered static and unchanging, with the Milky Way as the entire cosmos. This belief persisted until the early 1920s, when a series of discoveries challenged this view and shook the foundations of astronomy. In 1924, astronomer Edwin Hubble, using the newly built 100-inch Hooker telescope at Mount Wilson Observatory, made a discovery that would change our understanding of the universe forever. Hubble observed that the Andromeda Nebula, previously thought to be part of the Milky Way, is in fact a galaxy of its own, millions of light-years away. This realization expanded the known universe from a single galaxy to a vast cosmos full of countless galaxies. But Hubble didn't stop there. In the following years, he observed that almost all galaxies were moving away from us, and their light showed a red shift, a phenomenon in which the light stretches to longer, redder wavelengths as an object moves away. The further away a galaxy was, the faster it seemed to recede. This led to the groundbreaking conclusion that the universe is expanding, a concept that would become the cornerstone of modern cosmology. Hubble's observations provided strong evidence for the Big Bang theory, a model that proposes that the universe began as a hot, dense point some 13.8 billion years ago and has been expanding ever since. This discovery was monumental, not only because of its scientific importance, but also because of the profound philosophical change it required. Humanity had to accept that the universe was far larger and more dynamic than previously thought. In 1964, another groundbreaking discovery was made that further substantiated the Big Bang theory. Arno Penzias and Robert Wilson, while working at Bell Labs in New Jersey, accidentally detected a faint, persistent noise in their radio antenna. This noise, they discovered, did not come from a known source on Earth, but was rather a cosmic signal that permeates the entire universe. This signal, known as the cosmic microwave background radiation, CMB, is the afterglow of the Big Bang, the heat left over from the fiery birth of the universe. The CMB provides a snapshot of the universe when it was only 380,000 years old, allowing scientists to study the conditions of the early universe in minute detail. The discovery of the CMB was monumental evidence for the Big Bang theory, confirming that the universe had indeed begun in a hot, dense state. The CMB also revealed subtle temperature variations that correspond to the nuclei of galaxies and large-scale structures that we observe in the universe today. These tiny fluctuations, engraved in the CMB, were crucial to understanding how the universe evolved from a smooth, steady state to the complex cosmic web of galaxies we see today. Launched in 1999, the Hubble Space Telescope is one of the most transformative scientific instruments in history. Named after Edwin Hubble, this space-based observatory has provided a wealth of data that has deepened our understanding of the cosmos. Unlike ground-based telescopes, which are affected by the Earth's atmosphere, Hubble operates in the vacuum of space, delivering unprecedented clarity and detail. One of Hubble's most significant contributions was his role in determining the rate of expansion of the universe, known as the Hubble constant. By observing distant galaxies and measuring their redshifts, Hubble enabled astronomers to refine their estimates of the age of the universe and its rate of expansion. In addition, Hubble has captured breathtaking images of distant galaxies, nebulae, and star clusters, giving us an insight into the history and structure of the universe. These images have not only expanded scientific knowledge, but also inspired a broader appreciation of the beauty and complexity of the cosmos. While Hubble's discoveries have expanded our understanding of the universe, they have also highlighted some of its deepest mysteries. One of the most puzzling is the existence of dark matter and dark energy, which together make up about 95% of the total mass energy content of the universe. Dark matter, first proposed by Fritz Zwicky in the 1930s, is an invisible form of matter that does not emit, absorb, or reflect light, and is therefore undetectable with traditional telescopes. However, their existence is inferred from their gravitational effects on visible matter such as galaxies and galaxy clusters. Without dark matter, the observed rotation speeds of galaxies and the movements of galaxy clusters cannot be explained. Even more mysterious is dark energy, which was discovered in the year 1998 through observations of distant supernova. These observations showed that the expansion of the universe is not slowing down, as would be expected due to gravitational attraction, but is instead accelerating. This acceleration indicates the presence of a repulsive force dark energy that surpasses gravity on cosmic scales. Understanding dark matter and dark energy remains one of the greatest challenges of modern cosmology. At the forefront of our quest to understand the fundamental nature of the universe is the Large Hadron Collider, LHC, the world's largest and most powerful particle accelerator. Located at CERN, near Geneva, Switzerland, the LHC has been crucial to the study of the building blocks of matter and the forces that govern their interactions. In the year 2012, the LHC made headlines with the discovery of the Higgs boson, a fundamental particle that gives other particles mass. This discovery was a great triumph for the standard model of particle physics, a theory that describes the fundamental particles and their interactions. The Higgs boson, often referred to as the God particle, was the last missing piece of the standard model puzzle and confirmed a key aspect of our understanding of the fundamental structure of the universe. But the work of the LHC is far from over. Scientists continue to use the accelerator to search for new particles and forces, including potential candidates for dark matter. The discoveries made at the LHC could provide crucial insights into the nature of the universe and the underlying principles that determine its behavior. The early discoveries of the 20th century laid the foundations for modern cosmology and transformed our understanding of the universe from a static, unchanging cosmos to a dynamic, expanding universe full of unsolved mysteries. From Hubble's revelation of an expanding universe to the discovery of dark matter, dark energy, and the Higgs boson, these milestones have reshaped our view of the cosmos and opened up new avenues for exploration. The history of our universe is a story of continuous discovery, with each revelation leading to new questions and challenges. As we delve deeper into the cosmos, we realize again and again that the universe is far more complex and mysterious than we could ever have imagined. The mysteries of black holes and singularities. Black holes are among the most mysterious and fascinating objects in the universe. These cosmic giants are regions in space where gravity is so strong that nothing, not even light, can escape as soon as it crosses the event horizon. The study of black holes not only challenges our understanding of physics, but also extends the limits of our knowledge of the most extreme conditions in the universe. Black holes are formed from the remains of massive stars that have completed their life cycle. When a star has used up its nuclear fuel, it can no longer hold its own against gravity. In stars with a mass more than 3 times that of the Sun, This gravitational collapse is so overwhelming that it leads to the formation of a black hole. The process begins with the collapse of the star's core under its own gravity. As the nucleus shrinks, the temperatures and pressure rise to such an extent that the atoms inside are crushed and the protons and electrons fuse to form neutrons. This leads to the formation of a neutron star if the remaining nucleus remains below a certain mass. However, if the mass of the nucleus exceeds this limit, even the neutron degeneracy pressure, the force that prevents neutrons from being compressed further, cannot stop the collapse, which leads to the formation of a black hole. The boundary surrounding a black hole is called the event horizon. This is the point of no return. As soon as matter or radiation crosses this boundary, it is inevitably drawn into the black hole. The size of the event horizon is proportional to the mass of the black hole and is called the Schwarzschild radius. At the center of a black hole lies the singularity, a point at which the entire mass of the black hole is said to be concentrated. Here, the gravitational force is infinitely strong, and the curvature of space-time becomes infinite. The laws of physics as we know them break down at the singularity, making it one of the deepest mysteries of cosmology. The concept of the singularity challenges our understanding of the universe. According to Einstein's general theory of relativity, the singularity is a region in which the curvature of space-time becomes infinite, and the gravitational forces are so intense that they create a tear in the fabric of space-time. However, this theory does not take into account quantum effects, which play a role under such extreme conditions. Reconciling general relativity with quantum mechanics in the context of singularities is one of the biggest unsolved problems in physics. The singularity is also the place where the information paradox arises. According to quantum mechanics, information about the physical state of a system should never be lost. However, when matter falls into a black hole, it appears to disappear beyond the event horizon, which raises the question of whether the information is lost forever or somehow preserved. This paradox has triggered heated debates among physicists and remains an open question in theoretical physics. Black holes come in different sizes, which are mainly divided into stellar black holes, supermassive black holes, and intermediate mass black holes. Stellar black holes are the most common type and are formed from the remnants of massive stars, with masses ranging from a few to several tens of solar masses. These black holes are often found in binary systems where they interact with a companion star, accreting matter from it and emitting X-rays in the process. Supermassive black holes, on the other hand, are located in the centers of galaxies, including our own Milky Way. These colossal black holes have masses of millions to billions of solar masses. The origin of supermassive black holes remains an intensive research topic. Some theories suggest that they formed from the collapse of massive gas clouds in the early universe, while others propose that they grew from the merging of smaller black holes over time. One of the best-known supermassive black holes is Sagittarius A, which is located at the center of the Milky Way. This black hole has a mass of around 4 million solar masses and was first detected due to its gravitational influence on nearby stars. Despite its enormous mass, Sagittarius A is relatively quiet and emits low levels of radiation compared to more active galactic nuclei. Medium-mass black holes occupy an intermediate position, with masses ranging from hundreds to thousands of solar masses. These black holes are rarer and harder to detect. Their existence was deduced from observations of ultra-bright X-ray sources and gravitational wave events, in which the merging of smaller black holes could lead to the formation of an intermediate mass black hole. There is also the theoretical possibility of primordial black holes that could have been created in the early universe shortly after the Big Bang. These black holes would have very small masses, possibly even as small as a mountain, but with incredibly high densities. Primordial black holes could contribute to dark matter, although no clear evidence for their existence has yet been found. In 1974, physicist Stephen Hawking proposed a groundbreaking theory that combined quantum mechanics with the physics of black holes. According to Hawking, black holes are not completely black, but emit radiation due to quantum effects near the event horizon. This phenomenon, known today as Hawking radiation, arises from the interaction of virtual particle-antiparticle pairs that form spontaneously near the event horizon. In the vacuum of space, particle-antiparticle pairs are constantly forming and annihilating each other. However, near the event horizon of a black hole, one of these particles can be captured while the other escapes. The escaping particle becomes real, causing the black hole to lose a tiny amount of its mass. Over time, this process causes the black hole to lose energy and eventually evaporate completely. Hawking radiation has profound implications for our understanding of black holes and the nature of the universe. It suggests that black holes have a finite lifetime and will eventually evaporate, although for most black holes, this process would take longer than the current age of the universe. Hawking's work also contributes to the ongoing debate about the information paradox, as it raises questions about what happens to the information that falls into a black hole when the black hole eventually evaporates. In April 2019, the Event Horizon Telescope (EHT) collaboration made history by capturing the first image of a black hole. This black hole, which is located in the center of the galaxy M87, is a supermassive black hole with a mass of around 6.5 billion solar masses. The image, which shows a bright ring around a dark shadow, provided visual proof of the event horizon and was a monumental success in both astronomy and physics. The EHT is not a single telescope, but a network of radio telescopes spread across the globe, working together to create a virtual telescope the size of the Earth. By combining the data from these observatories, the EHT achieved the necessary resolution to detect the event horizon of a black hole, something that was previously considered impossible. The image of the black hole in M87 was a direct confirmation of many theoretical predictions about black holes, including the existence of the event horizon and the curvature of light around such a massive object. It also marked the beginning of a new era in astrophysics, in which direct observations of black holes could provide insights into their properties and the extreme environments near their event horizons. Another groundbreaking discovery in connection with black holes came in the year 2015, when LIGO, Laser Interferometer Gravitational Wave Observatory, detected gravitational waves for the first time. These waves were generated by the merger of two black holes, each of which had about 30 solar masses and were located over 1 billion light-years away. The detection of gravitational waves opened a new window on the universe and enabled scientists to observe cosmic events that are invisible in electromagnetic light. Gravitational waves are ripples in space-time that were predicted by Einstein's general theory of relativity. They are created by the acceleration of massive objects such as black holes or neutron stars and spread through the universe at the speed of light. The LIGO detectors, located in the United States, use laser interferometry to measure the tiny distortions in space-time caused by passing gravitational waves. Since its first discovery, LIGO and its European counterpart Virgo have detected dozens of gravitational wave events, many of which are associated with the merging of black holes. These observations have provided new insights into the population and properties of black holes, including their masses, angular momentum, and merging rates. Gravitational wave astronomy is still in its infancy, but holds enormous potential for discovering new physics and deepening our understanding of the universe. The concept of wormholes, also known as Einstein-Rosen bridges, is closely associated with black holes in theoretical physics. A wormhole is a hypothetical tunnel through space-time that could connect two distant points and potentially enable faster-than-light travel, or even time travel. Wormholes result from solutions to Einstein's field equations, which describe how matter and energy influence the curvature of space-time. In simple terms, a wormhole can be thought of as a shortcut between two regions of space-time. If a black hole represents a one-way exit from our universe, a wormhole could theoretically enable two-way travel between different regions of space or time. However, creating or maintaining a traversable wormhole would likely require exotic matter with negative energy density, something that has not yet been observed in nature. Wormholes remain a fascinating but speculative concept in physics. Although they are mathematically possible, no proof of their existence has been found, and they could remain purely theoretical. Nevertheless, the study of wormholes has inspired countless musings and discussions about the nature of space-time, causality, and the limits of human understanding. Black holes are among the most mysterious and extreme objects in the universe and challenge our understanding of gravity, space-time, and the fundamental nature of reality. From the formation of black holes and the concept of singularities, to the discovery of gravitational waves and the theoretical possibilities of wormholes, the study of black holes is pushing the boundaries of science and technology. The discoveries made in black hole physics not only deepen our understanding of the universe, but also raise profound questions about the nature of existence. As we continue to explore these cosmic mysteries, we are reminded that the universe is full of surprises, with each discovery leading to new secrets waiting to be unraveled. The mysterious dark matter and dark energy. In the great fabric of the universe, dark matter and dark energy are the invisible threads that hold the cosmic fabric together and stretch it. Together, they account for about 95% of the total mass energy content of the universe, but their nature remains one of the deepest mysteries of modern physics. This chapter explores the mystery of dark matter and dark energy, their discovery, the evidence for their existence, and the ongoing quest to understand these elusive components of the cosmos. The history of dark matter began in the 1930s with the work of the Swiss astronomer Fritz Zwicky. When studying the Coma galaxy cluster, Zwicky found that the galaxies within the cluster were moving much faster than expected if only the visible mass is taken into account. According to the laws of physics, the gravitational force of the visible stars and the gas should have been sufficient to hold the cluster together. But the galaxies were moving so fast that they were supposed to fly apart. To explain this discrepancy, Zwicky proposed the existence of an invisible form of matter that provided the gravitational force necessary to hold the galaxies together. He called this missing mass dark matter because it does not emit, absorb, or reflect light, and is therefore invisible to telescopes. Zwicky's hypothesis was initially met with skepticism, but further evidence accumulated over the following decades. In the 1970s, The American astronomer Vera Rubin provided some of the most convincing evidence for the existence of dark matter. Rubin studied the rotation curves of spiral galaxies, which show the speed of stars at different distances from the galactic center. According to Newtonian physics, stars that are further away from the center should orbit more slowly due to the decreasing gravitational force of the visible mass. But Rubin found that the stars in the outer regions of the galaxies orbited almost as fast as those closer to the center, suggesting the presence of a large amount of invisible mass that extends beyond the visible boundaries of the galaxy. These observations were consistent with the existence of dark matter, which exerts a gravitational effect but does not interact with electromagnetic radiation. Dark matter provides the additional gravitational force necessary to explain the observed rotation curves of galaxies, as well as the motions of galaxies in clusters and the behavior of light in gravitational lensing effects. Gravitational lensing is a phenomenon predicted by Einstein's general theory of relativity, in which the gravity of a massive object, such as a galaxy or cluster of galaxies, deflects light from a more distant object, such as a quasar or another galaxy. This deflection of light produces distorted, enlarged, or multiple images of the distant object as seen from Earth. Gravitational lensing effects have become a powerful tool for mapping the distribution of dark matter in the universe. As dark matter does not emit light, it cannot be observed directly. However, their gravitational effect can be demonstrated by their influence on the light of background objects. By studying the patterns of gravitational lensing effects, astronomers can deduce the presence and distribution of dark matter in galaxy clusters and large-scale cosmic structures. One of the best-known examples of gravitational lensing is the Bullet cluster, a collision of two galaxy clusters. Observations of the Bullet cluster showed that most of the mass was not associated with the visible matter in the galaxies or the hot gas, which emits X-rays, but was instead located in regions consistent with the distribution of dark matter. This provided strong evidence that dark matter is a separate component of matter that interacts mainly through gravity. Gravitational lensing effects have also been used to study the cosmic web, the large-scale structure of the universe, formed by the distribution of dark matter in galaxies. By analyzing the weak lensing effect on distant galaxies, astronomers have been able to map the dark matter filaments that connect clusters of galaxies, revealing the complex and extensive network that forms the backbone of the universe. The nature of dark matter is one of the most pressing questions in astrophysics. Although its gravitational effects are well documented, the identity of dark matter remains elusive. Several candidates were put forward, each with their own characteristics and challenges. One of the leading candidates is the weakly interacting massive particle, WIMP. WIMPs are hypothetical particles that interact only through gravity and the weak nuclear force, which makes them difficult to detect. It is thought that they were produced in large quantities during the early moments of the universe and could make up the majority of dark matter. Experiments such as those conducted at the Large Hadron Collider, LHC, and in deep underground laboratories such as the Cryogenic Dark Matter Search, CDMS, aim to detect WIMPs by observing their rare interactions with ordinary matter. Another candidate is the axion, a hypothetical particle originally proposed to solve a problem in quantum chromodynamics, the theory of the strong nuclear force. Axions are very light and weakly interacting, which makes them another plausible candidate for dark matter. The search for actions involves using strong magnetic fields to convert actions into photons, a process that could be detected by sensitive instruments. In addition to WIMPs and axions, there are also massive compact halo objects, MACOs, which include objects such as brown dwarfs, neutron stars, and black holes that are not massive enough to be easily detected by traditional observational methods. MACOs could contribute to dark matter, but they are probably not present in sufficient quantities to explain all dark matter. Despite intensive searches, none of these candidates have yet been definitively proven, which leaves the question of what dark matter is made of unanswered. The search continues with more sensitive detectors, larger experiments, and new theoretical models that could eventually reveal the nature of this mysterious substance. While dark matter is responsible for holding galaxies and clusters together, dark energy is seen as the driving force behind the accelerated expansion of the universe. The discovery of dark energy in the late 1990s was one of the most unexpected and profound revelations in cosmology. In 1998, two independent teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, studied distant Type Ia supernovae to measure the rate of expansion of the universe. Type Ia supernovae are considered standard candles because they have a consistent intrinsic brightness, which allows astronomers to determine their distance by measuring their apparent brightness. The teams expected to find that the expansion of the universe was slowing down due to the gravitational force of matter. Instead, they found that the supernovae were fainter than expected, indicating that they were further away than predicted. This implied that the expansion of the universe is not slowing down, but is actually accelerating. To explain this acceleration, cosmologists have proposed the existence of a mysterious force known as dark energy, which acts as a kind of anti-gravity that drives galaxies apart. It is now assumed that dark energy accounts for around 70% of the total energy density of the universe and is the dominant force driving the expansion of the cosmos. The simplest explanation for dark energy is the cosmological constant, a concept originally introduced by Einstein in his equations of general relativity to allow for a static universe. When it was discovered that the universe was expanding, Einstein famously called the cosmological constant his greatest mistake. However, the concept has been revived in the context of dark energy, where the cosmological constant is a constant energy density that fills space uniformly. In this model, dark energy is associated with the energy of the vacuum, the energy inherent in empty space itself. As the universe expands, the amount of dark energy increases and drives the accelerated expansion. This model has been successful in explaining a variety of cosmological observations, including the cosmic background radiation, the large-scale structure of the universe, and supernova data. However, the cosmological constant is not the only possible explanation for dark energy. Another leading theory is the quintessence, which proposes that dark energy is a dynamic field that changes over time and space. Unlike the cosmological constant, which is fixed, the quintessence could evolve and potentially lead to different scenarios for the future of the universe, including the possibility of the accelerating expansion slowing down or even reversing. Other theories propose modifications to the general theory of relativity or new forms of matter and energy that could explain the observed acceleration. These include theories of modified gravitation, additional dimensions, and variable fundamental constants. Each of these theories offers different predictions and challenges for cosmologists, and ongoing observations and experiments aim to test these ideas. The discovery of dark energy has profound implications for the ultimate fate of the universe. Different scenarios are possible depending on the properties of the dark energy. One possibility is the Great Freeze, in which the universe expands at an increasing rate, leading to a future in which galaxies move so far apart that they become invisible to each other. Star formation would cease, and the universe would become increasingly cold and dark until it reached a state of maximum entropy. Another scenario is the Great Rift, which would occur if the repulsive force of the dark energy increases over time. In this model, the expansion of the universe accelerates to such an extent that it tears apart galaxies, stars, planets, and ultimately even atoms. The universe would end in a catastrophic dissolution of all matter. Alternatively, if dark energy is not a cosmological constant but a dynamic field, it could change over time, possibly leading to a great collapse. In this scenario, the expansion of the universe could eventually slow down and reverse, leading to a contraction that ends in a collapse of the universe into a singularity, possibly followed by another Big Bang. The fate of the universe remains one of the most fascinating questions in cosmology. Ongoing observations, particularly those related to cosmic background radiation, large-scale structure, and distant supernovae, aim to refine our understanding of dark energy and its role in shaping the future of the cosmos. Dark matter and dark energy are the hidden forces that determine the behavior of the universe on the largest scale. While dark matter holds galaxies together, dark energy drives the accelerated expansion of the cosmos. Together, they make up the majority of the mass energy content of the universe, but their nature remains one of the greatest mysteries of science. The study of dark matter and dark energy not only challenges our understanding of fundamental physics, but also raises profound questions about the nature of the universe and its ultimate fate. As scientists continue to explore these elusive components, we realize once again that the universe is full of unknowns, and each discovery opens up new avenues of exploration and investigation. The multiverse hypothesis and the nature of reality. As our understanding of the universe has grown, the concept of the multiverse has become one of the most fascinating and controversial ideas in modern cosmology. The multiverse hypothesis states that our universe is possibly just one of many, perhaps even infinitely many each, with its own unique physical laws, constants, and conditions. This chapter examines the origins of the multiverse theory, the scientific foundations that support it, and the profound implications it has for our understanding of reality. The idea of multiple universes has its roots in ancient philosophy, but it gained scientific importance in the 20th century through developments in quantum mechanics, cosmology, and string theory. Several different models of the multiverse have been proposed, each emerging from different areas of physics. One of the earliest scientific indications of the possibility of a multiverse comes from quantum mechanics, in particular the many worlds interpretation, MWI. This was proposed in 1957 by physicist Hugh Everett and states that every possible outcome of a quantum mechanical event actually occurs, with each outcome creating a new, parallel universe. In this view, the universe is constantly branching out into multiple, non-communicating realities, each of which represents a different outcome of quantum events. Another important development in the concept of the multiverse comes from cosmic inflation, a theory proposed by Alan Guth in the early 1980s to explain the uniformity and flatness of the universe. According to the theory of inflation, the universe underwent a rapid and exponential expansion immediately after the Big Bang. This expansion may have created pocket universes, each with its own characteristics within a larger multiverse. String theory, which attempts to unify all the fundamental forces and particles of the universe by assuming that they are made up of tiny, vibrating strings, also provides a framework for the multiverse. String theory proposes the existence of several dimensions beyond the familiar 3 dimensions of space and 1 dimension of time. In some versions of string theory, different regions of space could have different configurations of these dimensions, which would lead to the emergence of different universes with varying physical laws. The concept of the multiverse comprises several different models, each based on a different theoretical framework. These models can be roughly divided into 4 main types, as described by physicist Max Tegmark. This type of multiverse arises from the vastness of space itself. The observable universe, i.e., the area of space from which light has been able to reach us since the Big Bang, is only a small part of a much larger, possibly infinite universe. In this model, regions of space far beyond our observable horizon could have different initial conditions, leading to the formation of different galaxies, stars, and planets. However, the physical laws and constants would remain the same in these regions. In the inflationary multiverse, different regions of space expand at different rates, creating separate bubble universes. These bubble universes could have different physical constants, particle types, and even dimensions, depending on the specific conditions in each region. This model suggests that our universe is just one of many bubbles in a vast multiverse, each with its own unique properties. The quantum multiverse arises from the many worlds interpretation of quantum mechanics. Every possible outcome of a quantum mechanical event creates a new, parallel universe. In this model, the multiverse contains an infinite number of parallel universes, each of which represents a different outcome of every quantum event that has ever occurred. These universes are constantly branching out, leading to an almost infinite number of possible realities. The ultimate multiverse, or mathematical multiverse, is the most speculative of the 4 types. It states that every possible mathematical structure exists as its own universe. In this view, our universe is just one of many possible mathematical structures that have physical existence. This model implies that the laws of physics themselves could be drastically different in different universes, with some universes operating under completely different principles. Although the multiverse remains a highly speculative idea, there are several lines of evidence and theoretical developments that support its existence. These include: one of the strongest arguments in favor of the multiverse comes from the theory of cosmic inflation. The rapid expansion of space during inflation could create separate regions with different properties, which could lead to the creation of several universes. Observations of the cosmic microwave background radiation, CMB, the afterglow of the Big Bang, provide indirect support for inflation. The uniformity of the CMB and the small temperature variations observed across the sky are consistent with the predictions of inflation theory. Some researchers have suggested that certain anomalies in the CMB, such as cold spots or unusual alignments, could be signatures of interactions between our universe and other bubble universes. The many worlds interpretation of quantum mechanics provides a theoretical framework for the quantum multiverse. Although direct evidence for parallel universes is lacking, the MWI is mathematically consistent with the observed behavior of quantum systems. Experiments in quantum mechanics, such as those involving quantum entanglement and superposition, reveal the strange and counterintuitive nature of reality at the quantum level, lending some credence to the idea that multiple outcomes could coexist in different branches of the multiverse. String theory, which requires additional dimensions, also supports the concept of the multiverse. In some versions of string theory, the shape and size of the additional dimensions determine the physical properties of the universe. Different configurations of these dimensions could lead to the creation of completely different universes, each with its own unique physical laws. Although string theory has not yet been confirmed experimentally, it provides a robust theoretical framework for the existence of a multiverse. The anthropic principle, which states that the universe appears fine-tuned for life because we are here to observe it, is often cited as a philosophical argument for the multiverse. In a single universe, the exact values of physical constants that enable the existence of life might seem improbable. However, in a multiverse with a large number of universes, each with different physical constants, it is not surprising that at least one universe, ours, has the right conditions for life. The multiverse offers a natural explanation for the apparent fine-tuning of the universe by suggesting that we live in one of the few universes where life is possible. The multiverse has profound implications for our understanding of reality, existence, and the nature of the universe. If the multiverse exists, it challenges the idea that our universe is unique or special. Instead, our universe could be just one of countless others, each with its own characteristics and possibilities. The multiverse raises profound philosophical questions about the nature of reality and our place in the cosmos. If every possible outcome of a quantum mechanical event creates a new universe, does that mean that every possible version of ourselves exists somewhere in the multiverse? What does this mean for the concept of free will if every possible decision we could make is realized in a branch of the multiverse? These questions challenge our understanding of identity, causality, and the nature of existence itself. The multiverse also raises questions about the limits of scientific knowledge. If other universes exist beyond our observable horizon, can we ever hope to discover or study them? Some physicists argue that the multiverse is not a scientific theory at all, as it may be impossible to test or disprove. Others suggest that indirect evidence, such as patterns in the CMB or the discovery of specific predictions from string theory, could support the multiverse. The debate about the scientific status of the multiverse touches on fundamental questions about the nature of science and the criteria for a valid scientific theory. At its core, the multiverse hypothesis challenges our understanding of what is real. If there are countless universes, each with its own version of reality, what does that mean for our concept of the universe as a single coherent entity? The multiverse suggests that reality is much more complex and diverse than we can imagine, with multiple layers of existence beyond our current understanding. The multiverse hypothesis is one of the most fascinating and controversial ideas in modern science. While it remains speculative, the multiverse has attracted serious consideration from physicists, cosmologists, and philosophers alike. Whether it is ultimately proven or remains a mind game, The multiverse challenges our understanding of reality and expands the boundaries of what we know about the universe and our place in it. As we continue to explore the possibilities of the multiverse, we realize that the universe, or multiverse, is far more mysterious and wondrous than we could have ever imagined. The search for answers to these profound questions drives the pursuit of knowledge and inspires us to explore the deepest mysteries of existence. The search for extraterrestrial life. The search for life beyond Earth has fascinated the human imagination for centuries. From ancient myths about gods and supernatural beings to modern scientific endeavors, the search for extraterrestrial life remains one of the most profound and enduring questions in science. This chapter looks at scientific efforts to discover life outside our planet, the conditions necessary for life to exist, and the implications of finding life elsewhere in the universe. In 1961, astronomer Frank Drake formulated an equation to estimate the number of active, communicative, extraterrestrial civilizations in the Milky Way. Known as the Drake equation, it serves as a framework for considering the various factors that would contribute to the existence of intelligent life capable of communicating across the vast distances of space. The Drake equation does not provide a definitive answer, but rather offers a way of structuring the search for extraterrestrial life. Each term in the equation represents a different aspect of the necessary conditions for life, and the values assigned to the terms are highly uncertain, reflecting our limited knowledge of the universe. Over the decades, as our understanding of the cosmos has grown, some of these terms have become better defined. We now know that planetary systems around stars are common, and that many exoplanets are located in the habitable zone of their star. However, the values for other terms, such as the fraction of planets on which intelligent life arises, remain speculative. One of the key factors in the search for extraterrestrial life is the concept of the habitable zone, also known as the Goldilocks zone. This is the area around a star where the conditions are just right for liquid water to exist on the surface of a planet, a crucial ingredient for life as we know it. A planet in the habitable zone is neither too hot nor too cold, and is therefore an important candidate for harboring life. The discovery of exoplanets within the habitable zone has been a major focus of astronomical research. The Kepler Space Telescope, launched by NASA in 2009, was specifically designed to find Earth-like planets in the habitable zones of their stars. During his mission, Kepler identified thousands of exoplanets, including several Earth-sized planets in the habitable zones of their stars. One of the most promising discoveries is Kepler 186f, an Earth-sized planet located about 500 light-years away in the constellation Swan. Kepler 186f orbits its star at a distance that allows for the possibility of liquid water on its surface, making it one of the best candidates for habitability among the exoplanets discovered so far. Another significant discovery is Proxima Centauri b, an exoplanet orbiting Proxima Centauri, the closest star to the Sun, just over 4 light-years away. Proxima Centauri b lies within the habitable zone of its star, raising the exciting possibility that it could harbor life. However, its proximity to a red dwarf star, which emits strong stellar flares, complicates the question of habitability, as these flares could strip off the planet's atmosphere. Detecting life on exoplanets requires more than just finding planets in the habitable zone. It also requires identifying biosignatures that are indicators of life and can be detected remotely. Biosignatures can include certain gases in a planet's atmosphere, such as oxygen, methane, or carbon dioxide, which are often associated with biological processes on Earth. One of the main goals of future space telescopes, such as the James Webb Space Telescope, JWST, and the planned Nancy Grace Roman Space Telescope, is to study the atmospheres of exoplanets and search for these potential biosignatures. By analyzing the light that passes through a planet's atmosphere as it passes its star, astronomers can determine the chemical composition of the atmosphere and look for signs that could indicate the presence of life. In addition to gases, potential biosignatures include surface features such as vegetation, which could be detected by specific reflectance patterns, or the presence of liquid water seas, which could possibly be inferred from the planet's albedo, reflectivity, and thermal emission. The search for biosignatures is still in its infancy, and detecting clear evidence of life on an exoplanet will be a significant challenge. But advances in technology and our understanding of planetary atmospheres are bringing us closer to the day when we may discover the first signs of life beyond Earth. Despite the vastness of the universe and the high probability of habitable planets, we have so far found no evidence of extraterrestrial civilizations. This disparity between the high probability of extraterrestrial life and the lack of observable evidence is known as the Fermi paradox, named after the physicist Enrico Fermi, who famously asked, "Where is everyone?" Several hypotheses have been proposed to explain the Fermi paradox. One possibility is that intelligent civilizations are rare, either because the conditions required for life are more stringent than we currently understand, or because the evolution of intelligent life is an extremely rare event. Another hypothesis proposes that intelligent civilizations may be self-destructive before they can establish interstellar communication or travel, due to factors such as nuclear war, environmental degradation, or uncontrollable technology. Alternatively, it is possible that extraterrestrial civilizations exist but deliberately avoid contact with us, perhaps following a prime directive of non-interference, similar to science fiction. This idea is sometimes referred to as the zoo hypothesis, which states that advanced civilizations observe us from a distance, much like humans observe animals in a zoo. Another explanation is that extraterrestrial civilizations may use forms of communication that go beyond our current technological ability to detect them. For example, they could use highly developed methods of communication, such as neutrino beams or quantum entanglement, which we have not yet discovered. After all, it is possible that we have not been looking long enough or in the right way. The vastness of the universe and the relatively short time we have been looking for extraterrestrial signals means that we may simply be missing the signs of extraterrestrial life. The search continues, and new methods and technologies could one day provide the answer to Fermi's question. While the search for biosignatures aims to detect life through its biological processes, the search for technosignatures aims to detect signs of advanced civilizations through their technology. Technosignatures could include radio signals, laser pulses, or other forms of electromagnetic radiation emitted by extraterrestrial civilizations. The best-known attempt to search for technosignatures is the Search for Extraterrestrial Intelligence, SETI, which began in the 1960s. SETI projects use radio telescopes to scan the sky for signals that could be artificial in origin, such as narrowband radio transmissions that do not occur naturally. Despite decades of searching, no definitive extraterrestrial signals have been detected, but the search continues with increasing sensitivity and sophistication. In recent years, the search for technosignatures has expanded to include other potential indicators of advanced civilizations. These include Dyson spheres, hypothetical structures that an advanced civilization could build around a star to harness its energy. The detection of an unusually large amount of infrared radiation from a star could indicate the presence of a Dyson sphere or other large-scale engineering projects. Other potential technosignatures include laser pulses that could be used to communicate over interstellar distances, and artificial satellites or spacecraft that could be detected by their reflected light or radio emissions. The discovery of technosignatures would be a monumental breakthrough and would provide direct evidence of intelligent life beyond Earth. While the search for extraterrestrial life is often focused on distant exoplanets, there are several promising candidates much closer to home. Mars, with its history of liquid water, has long been considered a prime candidate for past or present microbial life. The ongoing exploration of Mars by rovers, such as Curiosity and Perseverance, aims to discover signs of past life by analyzing the planet's rocks, soils, and atmosphere. In addition to Mars, the icy moons of the outer solar system are interesting targets in the search for life. Europa, a moon of Jupiter, is thought to have a subterranean ocean beneath its icy crust that is heated by tidal forces from Jupiter's gravity. This ocean could potentially harbor microbial life in environments similar to Earth's deep-sea hydrothermal vents. Similarly, Enceladus, a moon of Saturn, has geysers that spew water vapor and organic molecules from its underground ocean into space. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, discovered these fountains and provided evidence that Enceladus has the necessary ingredients for life, including water, organic molecules, and an energy source. Another fascinating target is Titan, Saturn's largest moon, which has a dense atmosphere rich in organic compounds and liquid methane lakes on its surface. Although the surface conditions on Titan are extremely cold, some scientists speculate that life could exist in its subsurface ocean of water and ammonia, or even in the methane lakes, based on a different chemistry than life on Earth. Future missions to these moons, such as the Europa Clipper and Dragonfly, are planned to further investigate their potential for habitability. These missions aim to explore the subsurface oceans and surface environments of these moons, looking for signs of life or the conditions that could support it. The discovery of extraterrestrial life, whether microbial or intelligent, would have profound implications for our understanding of the universe and our place in it. It would confirm that life is not limited to Earth, and that the processes that led to the emergence of life here could be common throughout the cosmos. Such a discovery would also raise important questions about the nature of life and the diversity of life forms that could exist. If we find life that is fundamentally different from life on Earth, perhaps based on a different biochemistry or living in extreme environments, it could expand our understanding of what life is and how it can emerge. The discovery of intelligent extraterrestrial life would be even more profound and would challenge our assumptions about our uniqueness in the universe. It would also raise complex ethical, philosophical, and theological questions about how we should interact with other intelligent beings and what it means to be part of a larger cosmic community. The search for extraterrestrial life is not only a scientific endeavor, but also a search for the fundamental nature of life, the universe, and our place in it. As we continue to explore space, we may one day realize that we are not alone, a realization that would change our view of the universe forever. The search for extraterrestrial life is one of the most exciting and profound endeavors of modern science. From the discovery of exoplanets in the habitable zone to the search for biosignatures and technosignatures, scientists are exploring all possible ways to discover life beyond Earth. Although we have yet to find definitive evidence of extraterrestrial life, the search continues, driven by the fundamental human desire to understand our place in the cosmos. The implications of finding life elsewhere in the universe are enormous and could reshape our understanding of biology, evolution, and the nature of life itself. As we continue to explore the universe, we realize that the cosmos is vast and full of possibilities, and the discovery of life beyond Earth could be just around the corner. The cosmic web and the large-scale structure of the universe. The universe is a vast and complex network of galaxies, connected by filaments of dark matter and gas that form a cosmic web stretching over billions of light years. Understanding this large-scale structure is crucial to understanding the development and dynamics of the cosmos. This chapter explores the formation of the cosmic web, the role of dark matter in shaping the universe, and the methods astronomers use to map this colossal structure. The origins of the cosmic web can be traced back to the beginning of the universe, to a time shortly after the Big Bang. In the first moments of the universe's existence, it was a hot, dense, and almost uniform mush of particles and radiation. However, tiny quantum fluctuations in this original slurry led to slight density fluctuations, which later grew into the large-scale structures that we observe today. As the universe expanded and cooled, these small fluctuations became the seeds for the formation of galaxies, clusters, and the cosmic web. The process began with the recombination era, about 380,000 years after the Big Bang, when the universe had cooled down enough for protons and electrons to combine to form neutral hydrogen atoms. This made the universe transparent to radiation and released the cosmic background radiation, CMB, that we observe today. Over time, gravity amplified the small density fluctuations, causing regions with slightly higher densities to attract more matter. These regions began to collapse under their own gravity and form the first stars and galaxies. The gravitational force of dark matter, which makes up around 85% of the matter in the universe, played a decisive role in this process. Dark matter provided the framework around which normal matter could gather and form the structures we see today. When galaxies formed, they were not randomly distributed in the universe. Instead, they grouped together along the dense filaments of dark matter and formed a net-like structure. These filaments connect clusters of galaxies and are surrounded by wide, empty cavities in which only a few galaxies exist. We refer to this large-scale structure as the cosmic web. Dark matter is the invisible glue that holds the universe together. While it does not interact with light or other electromagnetic radiation, its gravitational influence is crucial in shaping the large-scale structure of the universe. Without dark matter, the observed distribution of galaxies and the formation of the cosmic web would be impossible. The presence of dark matter was first deduced from the rotation curves of galaxies, as already mentioned. However, their role in the large-scale structure became clearer through computer simulations and observations of galaxy clumping and gravitational lensing. These studies have shown that dark matter forms a vast network of filaments stretching across the universe, with clusters of galaxies located at the intersections of these filaments. N-body simulations are one of the most important tools used by cosmologists to study the role of dark matter in the formation of the cosmic web. These simulations model the gravitational interactions between a large number of particles, representing dark matter, over time, starting from the initial conditions after the Big Bang. By comparing the results of these simulations with observations of the real universe, scientists can gain insights into the distribution of dark matter and its influence on galaxy formation. One of the most famous simulations is the Millennium Simulation, which was carried out by the Virgo Consortium in the early 2000s. This simulation tracked the development of 10 billion particles over a space cube with an edge length of over 2 billion light-years. The results provided a detailed picture of the cosmic web and showed how dark matter and galaxies are distributed on the largest scales. Another important tool for studying the cosmic web is gravitational lensing. When light from distant galaxies passes through massive structures such as galaxy clusters, it is bent by the gravitational force of dark matter. By analyzing the distortions in the images of the background galaxies, astronomers can map the distribution of dark matter in the universe. This technique, known as weak gravitational lensing, has been used to create some of the most detailed maps of the cosmic web available to date. The cosmic background radiation, CMB, is the oldest light in the universe, a remnant from the time when the universe was only 380,000 years old. It provides a snapshot of the universe at this early time and allows scientists to study the conditions that led to the formation of the cosmic web and large-scale structure. The CMB is remarkably uniform, but it contains tiny temperature fluctuations that correspond to density fluctuations in the early universe. These fluctuations are the seeds of the cosmic web and represent regions of slightly higher or lower density that later grew into galaxies, clusters, and voids. The study of the CMB has been revolutionized by a series of space missions, including the COBE, Cosmic Background Explorer, WMAP, Wilkinson Microwave Anisotropy Probe, and Planck satellites. These missions have provided increasingly detailed maps of the CMB, revealing the small temperature fluctuations with unprecedented precision. The data from these missions have enabled cosmologists to refine their models of the early universe and the formation of the cosmic web. By comparing the observed CMB fluctuations with theoretical predictions, scientists have been able to confirm key aspects of the standard model of cosmology, including the role of dark matter and dark energy in shaping the universe. To study the cosmic web in detail, astronomers rely on large-scale surveys that map the distribution of galaxies over large areas of space. These elevations provide a three-dimensional picture of the universe and reveal the complex structure of the cosmic web. One of the most ambitious surveys is the Sloan Digital Sky Survey, SDSS, which has mapped the positions of millions of galaxies and quasars across a quarter of the sky. The SDSS has provided some of the most detailed maps of the cosmic web, allowing astronomers to study the distribution of galaxies, the clumping of dark matter, and the large-scale structure of the universe. Another important project is the Dark Energy Survey, DES, which aims to map the distribution of dark matter and galaxies over a 5,000 square degree area of the southern sky. The DES uses a powerful camera mounted on a telescope in Chile to observe hundreds of millions of galaxies and provide data that will help scientists understand the nature of dark energy and its influence on the cosmic web. These surveys are complemented by other observational efforts, such as the Baryon Oscillation Spectroscopic Survey, BOSS, which measures the large-scale distribution of galaxies to study the expansion of the universe and the effects of dark energy. By combining data from these different surveys, astronomers can create detailed models of the cosmic web and refine their understanding of the large-scale structure of the universe. The cosmic web consists of two main components: filaments and voids. Filaments are the dense, thread-like structures that connect clusters of galaxies and form the backbone of the cosmic web. They are rich in dark matter and gas and are home to most of the galaxies in the universe. Cavities, on the other hand, are vast, empty regions of space with very few galaxies. These cavities make up the majority of the volume of the universe, but are almost free of matter. The study of voids is important for understanding the overall structure of the universe and the distribution of dark matter. One of the most fascinating aspects of the cosmic web is the way galaxies, clusters, and dark matter are organized in these filaments and voids. The distribution of matter in the universe is not random, but follows a pattern determined by the initial conditions of the early universe and the subsequent growth of structure through gravity. The study of cavities and filaments has provided new insights into the nature of dark matter and dark energy. For example, the properties of the voids, such as their size and distribution, can provide clues about the nature of dark energy and the expansion of the universe. The structure of the filaments can also provide information about the distribution of dark matter and the formation of galaxies. The study of the cosmic web is at the dawn of a new era with the development of next-generation observatories and space missions. These new instruments will provide even more detailed maps of the large-scale structure of the universe, allowing scientists to explore the cosmic web with unprecedented precision. One of the most anticipated projects is the Euclid mission, a space telescope being developed by the European Space Agency, ESA, to map the geometry of the dark universe. Euclid will measure billions of galaxies across more than a third of the sky and create a three-dimensional map of the cosmic web. These data are used to study the nature of dark matter and dark energy and the formation and evolution of the large-scale structure. Another important project is the Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, LSST. This ground-based observatory in Chile will conduct a 10-year survey of the southern sky, taking images of the entire visible sky every few nights. The Ruby Observatory will create a detailed map of the cosmic web and track the movements of galaxies and dark matter over time. In addition to these observatories, future space missions such as the James Webb Space Telescope, JWST, and the Nancy Grace Roman Space Telescope will provide new insights into the formation and evolution of galaxies within the cosmic web. These telescopes will allow astronomers to study the early stages of galaxy formation and the role of dark matter in shaping the large-scale structure of the universe. The cosmic web is the grandiose structure that defines the universe on the largest scales. Formed by the gravitational force of dark matter, it is a huge network of galaxies, clusters, filaments, and voids stretching over billions of light-years. Understanding this structure is the key to understanding the evolution of the universe and the role of dark matter and dark energy in shaping its destiny. Through large-scale surveys, computer simulations, and next-generation observatories, scientists are gradually unlocking the secrets of the cosmic web. As we continue to explore this colossal structure, we gain new insights into the nature of the universe and the forces that determine its evolution. The cosmic web reminds us of the vastness and complexity of the cosmos, and the ongoing quest to map and understand it is one of the most exciting frontiers of modern astrophysics. The expanding universe and the Big Bang theory. The universe is not static, it is in a state of constant expansion, a fact that has reshaped our understanding of cosmology and the origins of everything we observe. The discovery of the expanding universe and the development of the Big Bang theory are among the most significant achievements of modern science. This chapter examines the evidence for the expanding universe, the implications of the Big Bang, and the ongoing quest to understand the beginning and evolution of the cosmos. The concept of an expanding universe was first proposed in the early 20th century, but it was Edwin Hubble's observations in the 1920s that provided the decisive proof. Using the powerful Hooker telescope at Mount Wilson Observatory, Hubble studied the light from distant galaxies and made a groundbreaking discovery. The light from these galaxies was redshifted, indicating that they were moving away from us. Hubble's observations led to the formulation of Hubble's law, which states that the speed at which a galaxy moves away from us is directly proportional to its distance from us. In other words, the further away a galaxy is, the faster it moves away. Hubble's discovery was monumental because it provided the first direct evidence that the universe is expanding. This expansion implied that the universe had a beginning, a point in time when all matter and energy were concentrated in a single point, leading to the development of the Big Bang theory. The value of the Hubble constant, H0, has been refined over the decades through observations from various telescopes and missions, including the Hubble Space Telescope. Determining the exact value of H0 remains a central goal of cosmology, as it provides crucial information about the age, size, and fate of the universe. The Big Bang theory is the leading explanation for the origin and development of the universe. According to this theory, the universe began about 13.8 billion years ago as a singularity, a point of infinite density and temperature. From this initial state, the universe rapidly expanded and cooled, leading to the formation of the fundamental particles, atoms, stars, galaxies, and eventually all the structures we see today. The term Big Bang was coined in 1949 by astronomer Fred Hoyle, originally as a derogatory term for a theory he rejected. However, the name stuck and has been the accepted name for the origin of the universe ever since. The evidence supporting the Big Bang theory is extensive and includes several important observations. The cosmic background radiation, CMB, is the afterglow of the Big Bang, the leftover heat from the hot, dense beginnings of the universe. Discovered 1964 by Arno Penzias and Robert Wilson, the CMB offers a snapshot of the universe when it was only 380,000 years old. The uniformity and slight fluctuations in the CMB support the Big Bang model, as they represent the initial conditions that led to the formation of galaxies and large-scale structures. The Big Bang theory predicts that the early universe underwent a brief period of nucleosynthesis during which the first atomic nuclei were formed. This process mainly produced hydrogen, helium, and small amounts of lithium. The observed abundances of these light elements in the universe are consistent with the predictions of Big Bang nucleosynthesis and provide strong evidence for the theory. As described in Hubble's law, the observation that galaxies are moving away from us in all directions supports the idea that the universe is expanding. This expansion is consistent with the Big Bang model, which states that the universe began in a hot, dense state and has been expanding ever since. The distribution of galaxies and galaxy clusters in the universe, which form the cosmic web, is consistent with the predictions of the Big Bang theory. The initial density fluctuations, as seen in the CMB, grew over time under the influence of gravity and led to the formation of the large-scale structures that we observe today. The Big Bang theory describes the general development of the universe, but leaves several important questions unanswered, especially about the very first moments of the universe's existence. One of the most significant developments in this area is the theory of cosmic inflation. Proposed by Alan Guth in 1980, the theory of inflation states that the universe underwent an extremely rapid expansion in the first fractions of a second after the Big Bang. During this short period, the universe expanded exponentially, increasing in size by a factor of at least 10 to the power of 26 in a fraction of a second. Inflation explains several important features of the universe that the original Big Bang model could not explain, including the CMB is remarkably uniform in temperature, even in regions of the sky that are too far apart to be causally connected, i.e., light has not been able to travel between them since the Big Bang. Inflation solves this problem by suggesting that these regions were once close to each other before they were quickly driven apart by inflation. Observations show that the universe is very close to being flat, i.e., the geometry of space is not significantly curved. Inflation predicts that any initial curvature was smoothed out by the rapid expansion, resulting in the nearly flat universe we observe today. Inflation also provides an explanation for the origin of the density fluctuations that grew into galaxies and galaxy clusters. During inflation, quantum fluctuations in the space-time structure were stretched to macroscopic scales and sowed the seeds for the formation of large-scale structures in the universe. Inflation theory has become an essential part of the standard model of cosmology, but it also raises new questions about the nature of the universe, including the possibility of a multiverse, as discussed in an earlier chapter. The ultimate fate of the universe depends on its overall geometry and the amount of matter and energy it contains. There are three main possibilities. If the universe has negative curvature, i.e., it is open, it will continue to expand forever, with galaxies moving farther and farther apart, and the universe becoming increasingly cold and empty. This scenario is often referred to as the Big Freeze, in which star formation finally ceases and the universe approaches a state of maximum entropy. If the universe has a positive curvature, i.e., it is closed, the expansion will eventually slow down, stop and reverse, leading to a big crunch. In this scenario, the universe would collapse back into a singularity, possibly leading to a new Big Bang in a cyclical model of the universe. If the universe is flat, as current observations suggest, it will continue to expand forever, but at a decreasing rate, asymptotically approaching a steady state. This scenario is consistent with the presence of dark energy driving the observed accelerated expansion. The discovery of dark energy has added a new level of complexity to these scenarios. Dark energy, which makes up around 70% of the energy density of the universe, acts as a repulsive force that counteracts gravity and drives the accelerated expansion of the universe. The nature of dark energy is not yet well understood, and its properties will ultimately determine the fate of the universe. Understanding the early universe also involves studying the formation of the first stars and galaxies, known as the cosmic dawn. These objects formed a few 100 million years after the Big Bang and ended the so-called dark ages of the universe, when the universe was filled with neutral hydrogen and there were no light sources. The first stars, known as population 3 stars, were massive and short-lived and consisted almost exclusively of hydrogen and helium. These stars played a crucial role in the ionization of the universe, a process that ionized the hydrogen gas and caused light to travel freely through space, ending the Dark Ages. The first galaxies formed from the gravitational collapse of gas clouds, seeded by the density fluctuations generated during inflation. These early galaxies were small and irregularly shaped and gradually merged over time to form the larger, more structured galaxies we see today. The search for the first stars and galaxies is a major goal of modern astronomy, and several upcoming telescopes are designed to explore this epoch of cosmic history. The James Webb Space Telescope, JWST, for example, is designed to observe some of the earliest galaxies and shed light on the processes that led to the formation of the first structures in the universe. To understand the evolution of the universe, it is helpful to look at a short timeline of the most important events. The Planck era, 10 to the power of minus 43 seconds after the Big Bang. The earliest moment in the universe in which all fundamental forces were presumably united. The exact physics of this era remain unknown. The epoch of the Great Unification. Within 10 to the power of minus 43 to 10 to the power of minus 36 seconds. The universe is cooling, and gravity is separating from the other fundamental forces. The strong nuclear force, the weak nuclear force, and electromagnetism remain united. The inflation epoch. A period from 10 to the power of minus 36 to 10 to the power of minus 32 seconds. A rapid exponential expansion of the universe occurs, smoothing out any initial irregularity and setting the stage for the formation of large-scale structures. Quantum fluctuations during this period are stretched to cosmic scales and set the seeds for the formation of galaxies. The quark epoch, 10 to the power of minus 12 seconds to 1 microsecond. The universe continues to cool and allows the quarks to combine to form protons and neutrons. The fundamental particles that make up matter begin to form. The Hadron epoch, 1 microsecond to 1 second. Protons and neutrons form atomic nuclei, but the universe is still too hot for these nuclei to capture electrons and form neutral atoms. The Lepton epoch, 1 second to 10 seconds. Leptons, like electrons and neutrinos, dominate the universe. As the universe cools, it reaches a temperature at which most lepton-antilepton pairs annihilate each other. The photon epoch, 10 seconds to 380,000 years. The universe is dominated by radiation, with photons scattered by free electrons in a hot, opaque plasma. This period ends with the recombination epoch, when electrons combine with nuclei to form neutral atoms and allow photons to travel freely, creating the cosmic background radiation. The Dark Ages, 380,000 years to 150 million years after the Big Bang. The universe is filled with neutral hydrogen and helium gas, without light sources. This period ends with the formation of the first stars and galaxies. The Cosmic Dawn, 150 million years to 1 billion years after the Big Bang. The first stars and galaxies form, reionize the universe, and end the Dark Ages. The first galaxies are small and irregular, but merge over time. The formation and evolution of galaxies, 1 billion years after the Big Bang. Galaxies continue to form and evolve, creating larger structures through mergers and accretion. The cosmic web of filaments and voids is more strongly defined by the gravitational influence of dark matter. The present, 13.8 billion years after the Big Bang. The universe continues to expand, driven by dark energy. Galaxies are distributed in a huge cosmic web in which stars form, age, and die. The universe is in a state of continuous evolution, with many unanswered questions about its ultimate fate. The discovery of the expanding universe and the development of the Big Bang theory have revolutionized our understanding of the cosmos. From the original singularity point to the formation of the first stars and galaxies, the universe has undergone a remarkable journey of evolution and transformation. The study of the expanding universe continues to provide new insights into the nature of reality, the origins of everything we observe, and the ultimate fate of the cosmos. As we continue to refine our measurements of the expansion of the universe, explore the earliest epochs of cosmic history, and investigate the mysteries of dark energy, we are getting closer and closer to answering some of the most profound questions in science. The story of the expansion of the universe is far from over, and each new discovery brings us one step closer to understanding the full splendor of the cosmos. The role of supernovae in shaping the universe. Supernovae are among the most powerful and spectacular events in the universe and mark the explosive death of massive stars. These cosmic explosions play a decisive role in the development of galaxies, the formation of elements, and the dynamics of the universe. In this chapter, we will examine the different types of supernovae, their importance in cosmic history, and the profound impact they have on the universe. Stars are formed from clouds of gas and dust known as nebulae, which collapse under the effect of gravity. As the cloud collapses, it heats up and nuclear fusion ignites in the core, leading to the birth of a new star. The star spends most of its life in a stable phase in which it fuses hydrogen into helium in its core, a process that produces the energy that makes stars shine. The fate of a star is determined by its mass. Low-mass stars, like our Sun, will eventually use up their nuclear fuel and shed their outer layers, leaving behind a dense core known as a white dwarf. Massive stars, on the other hand, experience a far more dramatic end. When a massive star has used up its nuclear fuel, it can no longer support itself against gravity. The core collapses and the outer layers of the star are violently ejected in a supernova explosion. This explosion can outshine an entire galaxy for a short time and release more energy than the Sun will emit in its entire lifetime. Supernovae are categorized into two main types based on their progenitors and the mechanisms that trigger the explosion: Type 1 and Type 2 supernovae. Type 1 supernovae occur in binary star systems in which one of the stars is a white dwarf. In a Type Ia supernova, the white dwarf accretes matter from its companion star. As the white dwarf increases in mass, it approaches a critical limit known as the Chandrasekhar limit, about 1.4 times the mass of the Sun. When the white dwarf reaches this limit, the pressure in its core becomes so intense that a carbon fusion ignites explosively, leading to a thermonuclear burnout. The entire white dwarf is destroyed in the explosion, leaving nothing behind. Type Ia supernovae are particularly important in cosmology because they are standard candles. This means that they have a consistent intrinsic brightness, which allows astronomers to measure their distance by observing their apparent brightness. Type Ia supernovae have been used to measure the expansion of the universe and were instrumental in the discovery of dark energy, as discussed in an earlier chapter. Type 2 supernovae occur in massive stars, typically with masses more than 8 times that of the Sun. These stars undergo a series of nuclear fusion reactions in their cores, producing heavier and heavier elements until they form an iron core. Iron can no longer release energy through fusion, so the core collapses under its own gravity when it is made entirely of iron. The core collapse triggers a supernova explosion in which the outer layers of the star are hurled into space. The core can collapse into a neutron star, or, if the star is massive enough, into a black hole. Type 2 supernovae are characterized by the presence of hydrogen in their spectra, which distinguishes them from Type 1 supernovae. The shock waves from Type 2 supernovae can trigger the formation of new stars by compressing nearby clouds of gas and dust. This process, known as triggered star formation, is one way in which supernovae contribute to the ongoing cycle of star birth and death in galaxies. One of the most important contributions of supernovae to the universe is the process of nucleosynthesis, the creation of new elements through nuclear reactions. During their lifetime, stars produce elements up to iron through fusion. However, heavier elements than iron require additional energy to form, which is provided by the intense conditions of a supernova explosion. In the moments before and during a supernova, a large number of nuclear reactions take place that produce elements such as gold, platinum, uranium, and many others. These heavy elements are hurled into space by the explosion and enrich the interstellar medium with the building blocks for planets, life, and future generations of stars. This process of supernova nucleosynthesis means that many of the elements found on Earth, and even in our own bodies, were forged in the heart of a supernova. The calcium in our bones, the iron in our blood, and the gold in our jewelry all come from these cosmic explosions. As Carl Sagan famously said, "We are made of stardust." Supernovae play a crucial role in shaping the structure and evolution of galaxies. The energy released in a supernova explosion can drive powerful shock waves through the interstellar medium and influence the formation of new stars and the distribution of gas and dust in a galaxy. In some cases, supernovae can trigger galactic winds, where the combined energy of many supernovae in a star-forming region blows gas out of the galaxy. These winds can regulate star formation by consuming the gas needed to form new stars, effectively stifling star formation in certain regions. Supernovae also contribute to the mixing and distribution of elements within galaxies. The heavy elements produced in a supernova are distributed throughout the galaxy, enriching the interstellar medium and contributing to the chemical evolution of the galaxy. This process ensures that subsequent generations of stars and planets are richer in heavy elements than their predecessors. In addition, supernovae can influence the dynamics of the galaxy by injecting energy into the surrounding gas, creating turbulence and affecting the rotation and structure of the galaxy. The cumulative effect of many supernovae over billions of years has played a significant role in shaping the galaxies we observe today. After a supernova explosion, the ejected material expands and interacts with the surrounding interstellar medium, creating a supernova remnant. These remnants are often observed as luminous clouds of gas and dust, illuminated by the shock waves of the explosion. One of the most famous supernova remnants is the Crab Nebula, the result of a supernova observed by Chinese astronomers in the year 1054. The Crab Nebula is a luminous remnant of the explosion with a rapidly rotating neutron star known as a pulsar at its center. Supernova remnants provide valuable information about the explosion itself and the properties of the progenitor star. By studying the composition and motion of the ejected material, astronomers can learn more about the processes that took place during the explosion and investigate the role of supernovae in enriching the interstellar medium with heavy elements. Supernova remnants also play a role in the acceleration of cosmic rays, high-energy particles that travel through space at almost the speed of light. Shock waves from supernova remnants are considered to be one of the main sources of cosmic rays that can influence the chemistry of planetary atmospheres and the dynamics of the interstellar medium. Supernovae were crucial to the evolution of the universe, influencing everything from the formation of elements to the dynamics of galaxies. They are responsible for creating the heavy elements that make up planets, life, and many of the materials we use every day. Without supernovae, the universe would be a far less interesting place, consisting mainly of hydrogen and helium. Supernovae have also played a key role in shaping the large-scale structure of the universe. The energy they release drives the processes of star formation and galaxy evolution and influences the distribution of matter and the formation of structures within galaxies. In a broader sense, supernovae have contributed to the ongoing cycle of birth, death, and rebirth that characterizes the universe. They are both the end of a star's life and the beginning of new generations of stars and planets. In this way, supernovae are a fundamental part of cosmic history, linking the life cycles of stars to the evolution of galaxies and the universe as a whole. Supernovae are among the most powerful and influential events in the universe, marking the dramatic end of massive stars and playing a crucial role in the evolution of galaxies and the cosmos. From the formation of heavy elements to the dynamics of galaxies, supernovae have shaped the universe in profound ways. As we continue to study these cosmic explosions, we are gaining new insights into the life cycles of stars, the chemical evolution of galaxies, and the processes that have shaped the universe over billions of years. Supernovae remind us of the interconnectedness of the cosmos, where the death of a star can enable the formation of new stars, planets, and even life itself. The study of supernovae is a window into the ongoing processes that have made the universe what it is today, a dynamic, ever-evolving web of matter and energy.